Yeah, so I'm going to be talking about circulation overturning in eastern North Atlantic subpolar gyre. And this is the kind of final part of my PhD research that I just graduated this past December from Erasmus, and I'm sticking around for a little bit as a postdoctoral researcher. I want to present just the kind of final part of my PhD work. And so what I did was I looked at this region here, just in the eastern subpolar gyre to the east of the Reykjanes Ridge, north of the OSNAP line, which is marked in the triangles, and then south of the Iceland-Scotland Ridge. And I took the OSNAP results that we've gathered so far, some analysis done over the Reykjanes Ridge, and some historical estimates over the Iceland-Scotland Ridge to try to determine a mass budget and an overturning budget. So this was the final part of my PhD work, as I mentioned, where I produced some of these values and then looked at the other estimates from the OSNAP program. So what I did was I took this region and separated it into three sections. The first section is in red there, and these are waters that are lighter than 27.56. 27.56 is the isopycnal of maximum in the overturning stream function, as determined by the OSNAP program from Feli Lee's objective analysis in OSNAP East, so just between Greenland and Scotland. So everything in red here is considered the upper limb of the AMOC. And then the other two layers, the blue and the purple, are the lower limb. I separated the lower limb into those two densities with 27.8, separating those two water masses because waters that are more dense than 27.8 are sort of the formation waters of North Atlantic deep water, Iceland-Scotland overflow water in particular in this region. And the blue is more of the kind of cooler recirculating subpolar gyre water. So it made sense, I think, to try to separate those and look at all three water masses. And so what I found when I put it all together was from part of my research, I looked at the North Atlantic current flowing into the Iceland Basin and found that there's about 13 sphere drips of transport there, kind of half and half, a little bit more in maybe 60% in the upper layer, upper limb. And then another part of my research during my PhD time is that the East Reykjanes Ridge current has about 12 sphere drips of water exiting kind of in the southwest there, those values in the very bottom left corner. And I also found that, using Argo data, and altimetry, that there's about 7 sphere drips of water that flows over the Reykjanes Ridge. And that was a paper I published last year. And then other members of the OSNAP program, Manish talked earlier, and working with Bill Jones, my advisor, that ISO here in the bottom part of the lowest layer of the Iceland Basin has a net of about 5.3 sphere drips. Other OSNAP contributors, in particular, Louis Hopert and Stuart Cunningham, did a lot of the analysis in the Rockall region here. And so they have these values over the Rockall plateau from a year-long glider survey, or kind of intermittent year-long glider survey, and then 4 years of OSNAP data through the Rockall. And then finally, local estimates found that there's about 3 sphere drips of overflow entering this region and about 6.5 sphere drips exiting further north of this North Atlantic current water to eventually kind of cool and turn into overflow water. So if we add this all up, there's a bit of a mass discrepancy of about 5 sphere drips. And so I'm not going to go into all the details, and this is just a 10-minute presentation, but through using Yamaha drift displacement data and Argo data, using the OSNAP objective analysis, again, in collaboration with Feli Lee, we kind of determined that this location here, plateau, was where a lot of this discrepancy can be accounted for, and that this value, instead of about 4.5 sphere drips, would really be almost double, pretty close to 9 sphere drips of transport entering the basin or entering the region. And we kind of, our final number was about 30 sphere drips of total input and output to balance our mass budget in this region. So with that done, we were able to then take a look at overturning in the eastern subpolar gyre. So our analysis found that of the 30 or so strips of input, most of it, as you would probably expect, comes in from the south via the North Atlantic current, about 27 sphere drips or so, and there's a little bit of ISO recirculation, as you can see there. Once we account for the exchanges over the Iceland-Scotland ridge, the mass balance loses about 3 sphere drips, more water exiting the system than entering. An analysis by Bill Johns found that some of that overflow water that enters into the Iceland Basin entrains water from the upper layer and intermediate layer, and and so it increases the ISO volume, but also results in an overturning of 1.5 sphere drips there of water from the upper limb moving directly to my deepest layer here. And then when we exit the basin, from my work with the East Reconus Ridge current and over the Reconus Ridge, we have about 24 sphere drips leaving the system. But you might notice that from the upper layer in the very top left of this table to the intermediate layer, the bottom middle of this table, there's been a water mass transition through progressive water mass modification of about 6 sphere drips, or 6.2 in this case. And this is essentially due to atmospheric cooling, wintertime deep convection of the warm, salty North Atlantic current water, progressively becoming more dense and exiting essentially through the intermediate layer by the time it leaves this region. And if we add that 6.2 sphere drips to the 1.5 sphere drips that Bill found in his entrainment, we end up getting a total of nearly 8 sphere drips of over occurs in the eastern subpolar gyre to the east of the Reykjanes Ridge between the OSNAP line and the Iceland-Scotland Ridge. If we look at the other regions outlined in this image, historically, about 6 sphere drips of overturning occurs in the Norwegian Sea. That overflow water enters back into the subpolar gyre, kind of equally to the east and west of Iceland. And then that leaves only about 3 sphere drips of overturning in the Erminger Basin. And this is based on a total of 16.7 sphere drips, which again is the total from the OSNAP program in OSNAP East. And if we break that up just by percentages, that means that we have 1/6 of the overturning in the Erminger Basin, about 1/3 in the Norwegian Sea, and then nearly half of the Atlantic Meridional overturning circulation north of the OSNAP East line occurring in this relatively small region east of the Reykjanes Ridge. So finally, to try to verify this, I did a similar analysis in the Erminger Basin. That's the region that we have more OSNAP data and my estimates over the Reykjanes Ridge and some more historical data that's decently well known between Greenland and Iceland. And so I did the same sort of analysis there, just looking at the upper limb and lower limb. So I'm not doing the 3 different layers this time because I was trying to keep it a little bit more simple. And a good number of values just popped up there, but like I said, the values at the bottom are from SNAP objective analysis over the Reykjanes ridges from my analysis, and then the exchanges over the ridge there are from historical values. And we once again have a bit of a transport discrepancy, but if I just go ahead and without trying to account for where this discrepancy is coming from, if I were to just go ahead and evenly distribute it to the inflow and the outflow, take 2 sphere drips away from the inflow, add 2 to the outflow, and then proportion it equally to what we have there through our observation, that would only result in about 2 sphere drips of overturning. And I actually also did it in a way so that if we take those 4 sphere drips of, that's 4 sphere drips discrepancy and try to create the most overturning possible, like we attribute it all to the upper limb or the lower limb, depending upon the input or the output, we would only get 3.2. So my value of 3 sphere drips there, while, initially when I did this analysis, it seemed low, it seems like historical data and the OSNAP results are essentially agreeing, and maybe even suggest it should be a little bit less. So that's the final part to my PhD work and just what I wanted to present today. So my conclusions are that the total North Atlantic current flow that's lighter than 27.8 flowing into the eastern North Atlantic subpolar to the east of the Reykjanes Ridge is nearly 30 sphere drips, 25 to 28 sphere drips. But the main conclusion is that the eastern subpolar gyre is an important location for progressive water mass modification. This is where these warm, salty waters from the North Atlantic current cool and gradually transform, more dense waters in the kind of upper part of the lower limb of the AMOC. And that process, along with the little bit of entrainment from the overflow, accounts for nearly 50%. And that's it. Thank you.
Thank you, Greg. Any questions for Greg at this point?
I have a question.
Go ahead.
Thanks, Greg. It is really interesting. I wanted to ask you about the breakdown of water mass transformation in the Erminger Basin, because you showed a really neat table for the Isen Basin. Is there any transformation into the bottom layer in the Erminger Sea? Because it seemed that further east it was upper to intermediate only. Did you find any evidence in the observations for bottom?
So for the Erminger Basin, I only, that was like a quicker analysis. My more thorough analysis was in the eastern part of the Subpolar Gyre. So for the Erminger Basin, I only looked at upper limb versus lower limb, but not necessarily if those 3 sphere drips or 2.2 sphere drips were moving in kind of like upper part of the lower limb or what, if it was similar to what was occurring in the eastern subpolar gyre. So I can't say for sure. But one thing that I did note was that one of the reasons that there doesn't seem to be much in the Erminger Sea is just if you look at the OSNAP values of just the water flowing in to the Erminger Basin, and we know a lot of this is recirculating water, but we already have a vast majority of water in the lower limb. So yeah, if there is some erosion, as I suggest there, tiny bit in the Erminger Basin, it's might be from the upper lower limb, but so much already is in the lower limb.
Great, thanks for clarifying.
Yeah.
Any other questions?
Hey, Greg, good talk. Can I ask a question real quick?
Yeah.
Can you go back to the table you had for the eastern side?
Mm-hmm.
So I was just thinking about it. So you had where you get loss in the upper layer due to entrainment. So when you're thinking about that, is that like all going from the upper layer into the deeper layer? Just like thinking about how entrainment works, it kind of seems like you get some more intermediate stuff too, right? Like it's not all going to go from the upper layer to the greater than 27.8 layer.
Yeah. So based on the analysis that Bill did, or you and Bill did, I know you were helping with him on some of that. But it was everything went. All the entrainment went into the bottom layer, 2 sphere drips, 1.5 was from the upper layer, and then 1/2 was from the intermediate layer. So it's interesting that, 75% of it or so was from the upper layer, but it's just, I think, probably just the start of that descent as it flows over the ridge there, or the.
Okay, yeah, I think I
goes into the basin.
Didn't understand the way you said it the first time. Thanks.
Yeah, sorry.
Oh, it was good. Good talk. Thanks.